Hello friends, I welcome you to my second lecture on Neumann series and resolvent kernel. In the last lecture we discussed one problem on the solution of Volterra integral equation of second kind by finding the resolvent kernel. Here I start with one more such example to make things more clear. Let us consider the equation by x equal to 1 plus x square integral 0 to x 1 plus x square by 1 plus t square by t dt. You can see that it is a Volterra integral equation of the second kind, and so we will solve this equation by first finding the resolvent kernel and then determining the solution of this differential equation, solution of this integral equation. So let us write. We will first find the iterated kernels. Let us recall that the iterated kernels kxt, k1xt is given by kxt, and we are given here kxt equal to 1 plus x square by 1 plus t square. The kernel of the integral equation is kxt, which is given as 1 plus x square by 1 plus t square. Then k2xt, we know that k2xt is given by integral t to x kxz into k1 zt dz. So we can write it as integral t to x kxz. Kxz will be 1 plus x square upon 1 plus z square into k1 zt. K1 zt is same as kzt, and kzt will be 1 plus z square divided by 1 plus t square into dz. So 1 plus z square will cancel with 1 plus z square, and 1 plus x square by 1 plus t square is independent of z, so we can write it outside. And what we get is integral t to x dz, which after integration gives us so thus we have obtained the second iterated kernel k2xt. Let us find k3xt also in a similar manner. So k3xt is given by integral t to x kxz into k2zt dz. This is equal to integral t to x kxz. Kxz is 1 plus x square by 1 plus z square, and then k2zt. So k2xt is this. When we replace x by z, we get k2zt. So 1 plus z square divided by 1 plus t square into z minus t dz. So again we will cancel this, and we will have 1 plus x square by 1 plus t square integral t to x z minus t dz. After integration here, what we have is 1 plus x square by 1 plus t square, and then z minus t whole square by 2. The evaluation of this will give us 1 plus x square by 1 plus z square 1 plus t square 1 plus t square, and then x minus t whole square by 2, which we can write as x minus t whole square by 2 factorial. You can continue this process. You can find k4xt similarly. You can see that it comes out to be 1 plus x square by 1 plus t square x minus t whole to the power 3 divided by 3 factorial. So generalizing we have thus k n x t is equal to 1 plus x square by 1 plus t square, and we have x minus t raised to the power n minus 1 over n minus 1 factorial. Now let us find the resolvent kernel R x t lambda. So thus the resolvent kernel is now you can see in the given integral equation lambda is equal to 1. So we have R x t 1 equal to sigma n equal to 0 to infinity lambda to the power n then k n plus 1 x t. So this is lambda is 1 here. So summation n equal to 0 to infinity, and then we have 1 to the power n, then k n plus 1 will be 1 plus x square over 1 plus t square x minus t raised to the power n divided by n factorial, and this is nothing but 1 plus x square by 1 plus t square and then e to the power x minus t. Sigma n equal to 0 to infinity x minus t raised to the power n by n factorial is e to the power x minus t. Now having found R x t lambda, R x t lambda we have found. Now let us find the solution of the given integral equation. So let us put the value of R x t lambda. Here the solution of the integral equation is given by Volterra integral equation of the second kind by x equal to f x plus lambda integral a to x R x t lambda f t dt. So let us put the values here. F x is equal to 1 plus x square, lambda is equal to 1, a is given to be equal to 0, so 0 to x, and R x t lambda we have found 1 plus x square by 1 plus t square into e to the power x minus t, and then we have f t is 1 plus x square dt. So what we get is 1 plus x square, f t is 1 plus t square. So this 1 plus t square and the 1 plus t square here will get cancelled, and we will have 1 plus x square integral 0 to x 1 plus x square e to the power x minus t dt, and this can be written further as 1 plus x square, 1 plus x square into e to the power x we can write outside, and we have to simply integrate 0 to x e to the power minus t dt. So what we get is 1 plus x square plus 1 plus x square e to the power x, and minus e to the power minus t integral 0 to x. So, we have 1 plus x square, 1 plus x square e to the power x, and then we have 1 minus e to the power minus x. So, what we have is we will cancel these two cancel, and we have so by x is equal to 1 plus x square into e to the power x is the solution of the given integral equation. Now, let us discuss how to find the solution of a Volterra integral equation of second kind when its kernel we take as kxt, to the kernel kxt is of a particular form. Let us say this is the equation by x equal to fx plus lambda times a to x kxt yt dt, and the kernel kxt is a polynomial of degree n minus 1 in t, so that we can always write it in the form a kxt equal to a naught x plus a1 x into x minus t and so on, a n minus 1 x over n minus 1 factorial x minus t to the power n minus 1. You can see that this since we have assumed kxt to be a polynomial in t of degree n minus 1, we can always write it in this form where the where it is a polynomial in t of degree n minus 1. Now, the coefficients akx here, the coefficients akx where k varies from 0 to n minus 1, they are continuous in the closed interval ab. Then in this case, it turns out that the resolvent kernel rxt lambda is given by 1 over lambda dn over dxn gxt lambda, and gxt lambda is a solution of this differential equation of nth order. So, dn g over dxn minus lambda a naught x dn minus 1 g over dxn minus 1 plus a1 x dn minus 2 g over dxn minus 2 and so on dn minus 1 an minus 1 x into g equal to 0. This is a nth order differential equation with variable coefficients, and the conditions on g are g at x equal to t is 0, the dg over dx at x equal to t is also 0, and n minus 2th derivative of g at with respect to x at x equal to t is 0, while n minus 1th derivative of g with respect to x at x equal to t is 1. And then the required solution is given by x equal to fx plus lambda times integral a to x rxt lambda ft dt as usual, as we have earlier seen in the how to find the solution once the resolvent kernel is known. So, by putting the value of the resolvent kernel rxt lambda here, we can then find the required solution of the given integral equation. Now, let us see how this method works by taking an example. So, let us say by x equal to 1 minus 2x minus 4x square, and we have integral 0 to x 3 plus 6 times x minus t minus 4 times x minus t whole square yt dt. So, here you can see that fx function is 1 minus 2x minus 4x square, lambda is equal to 1, the lower limit a is equal to 0, and kxt is 3 plus 6 times x minus t minus 4 times x minus t whole square, which is a polynomial in t of degree 2, and already it is written in the form in which we want kxt to be. So, we want kxt to be in the form a naught x plus a1 x x minus t a2x into x minus t whole square by 2 factorial. It is in that form already. So, here fx is this, lambda is 1, kxt is 3 plus 6 times x minus t minus 4 times x minus t whole square. So, let us compare it this form of kxt with the general form of kxt when it is a polynomial in t of degree 2. So, you can see that when we compare a naught x is equal to 3, a1 x is equal to 6 and a2 x is equal to minus 8. Okay, now rxt lambda will be d cube gxt lambda over dx cube. Why? Because here kxt lambda is a polynomial in t of degree 2. So, when it is a polynomial in t of degree n minus 1, the nth order differential equation in G we have. So, rxt lambda is d cube g x t lambda over dx cube, and lambda is 1, so we can also write it as d cube g x t 1 over dx cube. Now this gxt1 is a solution of this differential equation. So this is the third order differential equation, because n is equal to 3 here, and we have put the values of a naught, a1 and a2. So 3 d cube g over dx cube, we see that a naught x is equal to 3, a1 x is 6, a2 x is minus 8. So substituting these values, we get this third order differential equation with constant coefficients, and we know how to solve nth order differential equation with constant coefficients. So let us write it in the notation of d, where d is the derivative with respect to x. So d cube minus 3d square minus 6d plus 8, this differential operator operates on g equal to 0. So it is a homogeneous differential equation of third order with constant coefficients. Now the conditions on g are g is equal to 0 and dg over dx is equal to 0 at x equal to t, and d square g over dx square is 1 at x equal to t. Okay. Now we can write the auxiliary equation corresponding to this homogeneous equation. So auxiliary equation is m cube minus 3m square minus 6m plus 8 equal to 0, and you can check that m is equal to 1 minus 2 4, they are the values of m which satisfy this equation. Now since these three values are real and distinct, the solution of the this third order differential equation in g is written as g equal to a e to the power x, b e to the power minus 2x, c e to the power 4x. Now in order to use the conditions on g, let us differentiate it with respect to x. So we get dg by dx equal to a e to the power x minus 2b e to the power minus 2x, and we get 4c e to the power 4x, and when we differentiate it once more, we get d square g by dx square, which is a e to the power x plus 4b e to the power minus 2x plus 16c e to the power 4x. Now let us use the conditions on g. When you will use the conditions on g, the conditions on g are at x equal to t, g is 0, dg by dx equal to 0, and at x equal to t, second derivative is 1. If you use these three conditions on this on these three equations, okay, we shall arrive at the three equations in ABC. Solving those three linear equations in ABC, we get the values of ABC, and the values of ABC when we put in the expression of gxt, we get here the following expression of gxt lambda. Gxt1 is equal to minus 1 by 9 e to the power x minus t, 1 by 18 e to the power minus 2x plus 2t, 1 by 18 e to the power minus 4x minus 4t. Now we differentiate it once, okay, so we get g dash. In order to find why we are differentiating now, because we want to know what is the rxt lambda. We want to know rxt lambda, and for rxt lambda we need to know what is d cube gxt1 over dx cube. So we have already found gxt1, so we will differentiate it thrice and get rxt lambda. So gxt1 is this, let us differentiate it once, we get this expression, we differentiate it again, we get this expression, and when we differentiate it again, we get this expression. So this is third derivative of g xt1, and what we get is this. Now so this is nothing but we get rxt1, rxt1 is third derivative of gxt1. So with respect to x, so by x is equal to fx plus integral 0 to x rxt1 into ft dt. Ft is 1 minus 2t minus 4t square, and we put the value of rxt1 here. Now this you can take you can do the integration by parts here by simply taking e to the power x here outside in the first case. In the second, you can take e to the power minus 2x out. In the third integral, you can take e to the power 4x outside, and then you integrate by parts. Say for example, in the first case we will have to integrate e to the power minus t into 1 minus 2t minus 4t square with respect to t and put the limits 0x. In the second case, we will be integrating e to the power 2t into 1 minus 2t minus 4t square with respect to t, and then we put the limits, and here we will be integrating e to the power minus 4t into 1 minus 2t minus 4t square and put the limits. So after you integrate by parts these three terms, and substitute the limit and simplify, you will get by x equal to e to the power x. Now, let me tell you that this method you can see is very cumbersome. You have to first find the differential equation in G, then you have to solve the differential equation in G. The differential equation in G has variable coefficients, they are functions depending on x, and when we have variable coefficients, it is not easy to solve the differential equation. Here what happened that the coefficients of the differential equation in G turned out to be constant, so we could easily solve this differential equation, and then we use the conditions over G to determine gxt lambda, and once we determine gxt lambda, we have to differentiate, say for example in this case 3 times to arrive at rxt lambda, and then we integrate rxt lambda, then we put the value of rxt lambda in the in this equation and integrate, which is again a lengthy procedure. So if you solve this by using the Laplace transform technique, let us say for example this one, this differential this integral equation, let us solve by using the Laplace transform technique. What we will do, we have y x equal to 1 minus 2x minus 4x square integral 0 to x, and then we have 3 plus 6 times x minus t minus 4 times x minus t whole square by t dt. So you can compare this equation with by x equal to fx plus integral 0 to x k x minus t by t dt. This equation is of this form, and such equations are called as integral equations of convolution type. We shall be later on discussing in how to find the solution of integral equations of convolution type. What we do is we take the Laplace transform of both sides. Suppose we assume that Laplace transform of by x is by s, and then the Laplace transform of fx is fs, then we get by s equal to fs, and then Laplace transform of this. Laplace transform of this integral 0 to x k x minus t y t dt can be found by using the convolution theorem, and we get Laplace transform of k say kx into Laplace transform of by x, because in the convolution theorem we say that if the Laplace transform of two functions phi 1 x and phi 2 x exists, Laplace transform of phi 1 x is say phi 1 s, and Laplace transform of phi 2 x is phi 2 s, then the Laplace transform of their convolution is defined as say 0 to x, we can say phi 1 x minus t into phi 2 t dt is equal to phi 1 s into phi 2 s. So here we see that we have the convolution of two functions kx and by x here, and so we have, while taking the Laplace transform of this, we have written it as the product of Laplace transform of kx into Laplace transform of by x. But here we need to assume that the functions kx and fx, the functions fx and kx are such that their Laplace transforms exist, that means they are of exponential order. So once we assume that, then it turns out that the function by x is also of exponential order, and so we can write its Laplace transform. So once we have this, I can write this further as and then we can solve it for by s. By s will be equal to fs divided by 1 minus this, and after we have found by s, we can take the inverse Laplace transform. So then by x, the solution of the given integral equation is then L inverse of fs over 1 minus this, and you will see that we can easily find the solution of this differential equation, which was given by x equal to e to the power x if we apply this technique, and it can be obtained in just 5-6 steps. Here this is a very cumbersome method to find the solution of the integral equation, but it is a method which is, so it is purely of academic interest. But here we can assume kx this to be a polynomial of any degree, and that can be managed here also. So one can always use to find the solution of such an integral equation by applying the technique of integral equations of convolution type. Now let us see, there is another case here. Suppose the kernel kxt is a polynomial of degree n minus 1 in x, then we can always represent it as kxt equal to b naught t plus b1 t t minus x and so on bn minus 1 t over n minus 1 factorial into t minus x to the power n minus 1. You can see it is a polynomial in x of degree n minus 1. Now then the resolvent kernel rxt lambda of this equation of the Volterra integral equation 1 of the Volterra integral equation 1 is given by rxt lambda equal to minus 1 over lambda dn over dtn of h at h xt lambda, where h xt lambda is a solution of the differential equation this of nth order with variable coefficients, because b naught, b1, bn minus 1 they depend on t. So this is nth order differential equation homogeneous and it satisfies these conditions: h at t equal to x, dh by dt at t equal to x, dn minus 2 h over dtn minus 2 at t equal to x is 0, and n minus 1 is the derivative of h with respect to t at t equal to x is 1. And then we can find the, once we have these, we can find the solution of this differential equation h x t lambda, and once h x t lambda is known, we can differentiate it n times and multiply by minus 1 over lambda to get r x t lambda. R x t lambda then is used here in this equation to determine the solution by x of the given integral equation. Now let us take an example on this. Suppose by x is equal to cos x minus 2. So this is our function f x. You can see f x is equal to cos x minus 2, lambda is 1 here, and kxt is a polynomial in x of degree 1. So it can be treated by the second particular form. You can also regard kxt here as a polynomial in t of degree 1. So it is of the form 1 as well as of the form 2. So kxt is t minus x here. We assume kxt to be of the form b naught t plus b1 t into t minus x, because kxt we are assuming as a polynomial in x of degree 1 in x. So we can write it like this, and then we compare this given kxt with this standard form, and then we see that b naught t is equal to 0 and b1 t is equal to 1. Resolvent kernel rxt lambda will become rxt1 because lambda is 1 here, and it will be given by minus d square h xt1 over dt square, because kxt is a polynomial in x of degree 1. So we have second derivative. Now where h xt1 satisfies the second order differential equation, d square h over dt square plus lambda b naught t plus b1 t into h equal to 0, lambda is equal to 1 here, b naught t is equal to 0 here, b1 t is equal to 1. So this equation reduces to d square h by dt square plus h equal to 0. So this is a second order differential equation with constant coefficients, and the conditions imposed on h are h is equal to 0 at t equal to x, and dH by dt is equal to 1 at t equal to x. Now we know how to determine the solution of this differential equation with constant coefficients. So here we have the auxiliary equation m square plus 1 equal to 0, which has got two roots, plus minus I. So we have the corresponding solution here as hxt1 equal to a cos t plus b sin t. Now we determine dH by dt here, so minus a sin t plus b cos t, substitute t equal to x and put h is equal to 0 in this equation, and then we put here t equal to x and put dH by dt equal to 1. Solve these two equations for the values of a and b, substitute, and then we will see that hxt1 comes out to be sin t minus x. Okay, so then once we know hxt1, we can then differentiate twice hxt1 with respect to t, multiply by minus 1, we get rxt1. So rxt1 will be equal to sin t minus x, and then by x is equal to cos x minus 2, 0 to x sin t minus x cos t minus 2 dt. So you can integrate here, you can open this cos sin t minus x by the formula sin a minus b, you can open this, and then you can integrate by integrate by parts. You can see that the answer is by x equal to minus cos x minus sin x minus half x sin x. So what I would suggest that this is again, this method is of purely academic interest, otherwise we can always treat it as an integral equation of convolution type, and by taking by writing t minus x as minus times x minus t, so it is an integral equation of convolution type, and then we can solve it by taking the Laplace transform of both sides, the way we solve a integral equation of convolution type. So with this I would like to conclude my lecture. Thank you very much for your attention.